There is a right and a wrong way to say you are taking the derivative. If your instruction was to tell somebody to take the derivative of this function, and I would call it f or g, I don't care, what's the right way to say it? What's the verb to represent the act of taking a derivative? To differentiate. What's the wrong one that I hate and I wish I hadn't showed you, but it keeps showing back up over and over? Derive. What does it mean to derive something? Good. To see where a formula or something comes from. So, for example, the quadratic formula. I wasn't your algebra 2 teacher. I don't know if you did it, but do you guys agree that this is what a quadratic looks like? Plus c, theoretically. Now, if I wanted to do this and complete the square, it's kind of ugly, but we could do it. There's some wonky stuff. It's not our focus today. You may not remember all the little algebra that goes into it, but we wind up, once I solve this equation by completing the square, I wind up with this. Now, what we've done here is to derive the quadratic formula. We just completed the square and we derived it. And remind me one more time, deriving is fine and dandy, but what do we call the actual act of taking derivatives? Differentiate. So differentiation or differential calculus is what we've been focusing on. And the cool thing is that there's a variety of flavors of calculus, and we've only gotten the very first of them. But we're going to get a little bit of exposure into the second flavor today. So here we go. Without further ado, 4.8. We are going to have to find a shorthand for this, but we're going to be pretty, would say rigorous today with our definitions and stuff, very specific. So 4.8, we are going to be discussing antiderivatives. And beyond that, we're also going to start talking, and maybe not today, but antiderivatives and differential equations. All right. So if you are going to study engineering, you're going to study math, physics, anything like that, your next class will either be Calc 1 again, just as like a refresher, depending on how it goes for the AP test and stuff, or Calc 2 would probably be your very next math class. Now, what's really cool is that as you start Calc 2, you then start to transition into some other fields of math that you don't even know exist yet. One of those fields of math is called differential equations. And like differential equations are kind of the key to the universe, realistically, because if you can't find exact equations for stuff, but you know that stuff changes, like slopes do, like with differentials or derivatives, then we have a way to predict without ever actually knowing equations, which is unbelievably powerful. Now, we get there by, we need to be able to undo a derivative. And what do you think we're going to call it when we undo a derivative? It'd be taking the antiderivative. That makes sense, to undo it. Cool. So here we go. Let's just get started with this. And again, just let me know when it gets too blah, and we'll kind of kick into it. If I give you a function f, there's an f prime that exists for most of the time, right? So we're just going to make some like little intuition builders. For a nice function, and I'm just going to put that in quotations, for a nice, quote unquote, function, and we'll call this f of x, there is a corresponding f prime. And I'm just going to write that as f prime of x exists. Now, I'm going to stop there, and I'm going to give you like 20 seconds to chat. It's going to go really quickly. What do I mean, nice function? If a derivative exists, what makes a function nice enough for that to happen? 20 seconds, pair up. There's a few keywords that I'm looking for. Talk it out. You're going to use definition-y stuff. For its derivative to exist, it has to be continuous. Does it have to be defined? Yeah. So does the limit have to exist? So all that stuff is what we're using. Continuity and the limit existence. Like, that's it. Okay. For a nice function, f prime exists. What about the other direction? Can we go the other direction? Instead of going from f to f prime, is there a way to go from f prime back to f? Which is the exact opposite. So, well, let's think about that. It turns out, yes, is the quick answer. We can undo this. And I'm going to say, instead of undo, we can go from a function let's say f prime of x 2x, or 2f of x rather, as well. Now, in here, there is some pretty big stuff that we're going to have to work out at the beginning of chapter 5. We're just getting intro into it, but it's just a two-way street. Give me a function, I can find its derivative. Give me a derivative, I can find the function from which it came. That is the whole thing that we're looking at. Now, very specifically, and I'm going to undo those, I'm going to make just one more little asterisk so I can separate the two of them. I'm going to make a standout comment here. We typically call this function, and notation matters. When we write stuff, if I'm writing a capital F, which is going to feel really weird, I want you to write a capital F. Like, there's a reason that we do it. We're going to consider the function f of x, and we're just saying, hey, here's how we do it. F of x, capital F of x, is the function, such that if we were to take the derivative of this thing, we'll just say f of x is exactly equal to df dx. And again, like, it's weird, but the capitalization is very specific. I'm saying here's a function that if we take its derivative, we get the original f of x back. This is just a mathy version of our previous statement. Now, all of this stuff is just some basic, like, hey, it exists and all that good stuff. Let's get a formal definition, and it's where we'll actually start. So, questions, comments, thoughts before we get going? Okay, so in 4.8, our first main topic is going to be a definition, and we're actually just going to straight up define, like formally, what an antiderivative actually is. Now, the good news is some of you guys are aware of the existence of another word that might be a little shorter. I'm not using it yet. Anybody know the word that I'm not using? Sean already said it. Aisha, what do you think it is? It is integral. We're not there yet. I'm not going to call these integrals yet for a very particular reason, but it is where we're going. We are on the way to dealing with integrals, if you guys have seen that yet. So we'll just define this. An antiderivative, by definition, is a function, cap f, a function that we will call capital F, is, and we're going to make the claim, this is the antiderivative. And I'm going to put in parentheses an antiderivative, and maybe there's a difference. A function cap f is the or an antiderivative. I really wish we had some shorthand of another function. We'll call this lowercase f if, and I don't know why I had a comma, and I'm going to leave us here for just a moment. Capital F is the derivative of little f in one situation. Now, we said that I can go from f to f prime reasonably, right? Like, that's just regular differentiating. To go from some function f of x to f prime of x. This thing, f, is called the antiderivative if and only if we take f prime, and it turns out that f prime, cap f prime of x, is the exact same thing as f of x plus some number c. And this is going to be true. What does this symbol mean? For all, and I want somebody to read this statement to me here in just a second. What does the second half of this statement read? For all x, and we can just say in the, like it's implied that we're talking about a set, but I'm okay with that. For all x in the set of the DOM, domain of f. So for every value that works for f of x, it's going to have a corresponding part somewhere in its antiderivative. Now, getting here can be kind of ugly, but it doesn't have to be. Today it's going to be super informal. We will learn that there's some limits, luckily, that we get to do. If you guys are just bummed that we haven't been doing limits lately, we do get some more limits. We get some summations that show up with it. But for now, we're just going to think about these a little bit nicer. So we're going to ease into this real gently, and we're going to start with some easy examples. and see if we can't find some nice, easy antiderivatives. So check it out. On these, the wording is going to be wonky. What I want us to do is given some function f of x, and let's say that on A, f of x we'll say is the function 2x. I want us to find cap f. That's it. And I'm not going to give us any more guidance on this until we just start kind of playing around with it. Here's a question, and I'll wait till you guys are all written because I see people still writing. The way that we're going to think about this today is wonky. Does there exist a function whose derivative is 2x? And I think there's probably a couple of them, or infinitely many of them, maybe. But any gut feelings just right off the bat? Whose derivative is 2x? X squared works, right? Now, here's the weird part, and this becomes super duper important as we get going. I don't think you've really given me the whole answer. So I think it's natural that f of x could be 2x. Sorry, not 2x. What did you guys tell me? X squared. Does this have a derivative that is 2x? So I'm okay with that, but that's not the only one. Give me another function, and it's just going to be a slight change to this that works. Plus c. Now, good catch, because we had that here, right? If I put a plus 2, what's the derivative of the plus 2 going to do? It's gone, right? Because plus 2 would just go to 0. What if it's plus 3 or 4 or 5 or negative 7 or pi or e or ln 5? Does it really matter what the constant is? Because the derivative of that constant is always going to be what? 0. So it's always gone. So instead of just saying here's one of them and then here's another blah, 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 let's just say it's just plus this. And I'm going to use a capital C for this. For all constants C that are real numbers. If you give me any real number, its derivative is going to be 0, and this will work. We have just calculated our first antiderivative. Crazy challenging. Let's get a little bit of practice. Do you guys remember me ever stressing the importance of memorizing your derivatives? I mean, you should, because I gave you 3 or 4 versions of the quiz where you had to show me that you memorized the derivatives. All of a sudden, I mean, those have been important the whole time, but they're, I would argue, maybe more or just as important still right now. So I'm going to give you guys a couple more. I want you to try some. On B, let's look at this one. I'm going to get B and C up here, and I'm just going to be more casual. I'm just saying, given f of x is this, cosine x, I want you to try to find me f prime, or sorry, cap f. Find cap f. I'll give you one more here. Now, we don't have a formal way to find these other than think it out. I'm going to give you guys a couple minutes maximum. I'm going to pause the video here. If you're watching this on the road, please pause it and try to discuss this with your fellow raters. But I'll give you guys a moment and we'll come back together. Try them out in 3, 2, 1. When we're thinking about these, here's my suggestion. Especially from the beginning, B is going to be pretty nice. Whose derivative is cosine? Sine. So just by playing that little thought there, say what derivative is cosine? And you say, well, it comes from sine. So f of x equals sine x. Does any plus number still account? Does it still work? If I do plus 1 or 2 or 3 or pi or whatever? Cool. So what should I write? Plus c. Now, we can always check, and it's so nice and easy to check. If I want to know if I've really correctly done this, we'll just rely on the definition. Whatever I write here, how do I get back to the blue one? I should, no, don't say derive. You're going to make my head explode. Did you say derivative? Did you really? Okay, I misheard. My head probably won't explode. Let's just take the derivative of this. What's the derivative of sine? Okay, I'm right. Okay, easy. Does anything that we've worked with have this as a derivative? This is the natural log, and this one's easy to miss unless we see it. But let's just check. Well, f of x, if we just write it as the natural log of x, does it matter what I add to it? If I do plus 2 or 3 or -5, like it still zeroes out when I take the derivative. We have successfully completed 3 lovely antiderivatives. Super hard, right? All right, Isha, I'm going to put you on the spot here for a second. You were not super pleased with the thought of integrals the other day. We're not quite at integrals. Is this hard? Oh, it's pretty much an integral, right? Okay, deal. Feels okay, feels awful. Now, we could make them like they can get really bad really fast. Just yep, no, I'm slowing down too. We're not there yet. But here we go. What we want to really pick out of this is this lovely theorem. And I'm trying to see if we really need to make it go too crazy. I'm going to be much less rigorous than your textbook is with this one. And we're just going to make a nice observation we're going to call it a theorem with the understanding that it's not super duper rigorous. So here is a couple different things that I want to make sure that we look at. If you give me some derivative, or some antiderivative rather, and we'll just call this a theorem with the understanding that much less rigorous just to save a little time. And I know I've said that like 5 times, but here we are. For this, if you give me cap f and lowercase f, I have a function and its antiderivative. We're just going to say cap f of x is the family of all functions whose derivative is equal to f of x. Now, when we do just a standard antiderivative, we are getting a whole big, infinitely large family of functions. So as we're looking at these, I just want to make sure we can see where these infinitely many families come from, or infinitely many functions. So let's do one more, and we're going to think not only just about how do we do it here, but I want to think about what the graphs actually look like to drive this family idea home. So on our next example, we're going to use this idea here and see if we can't make like larger sense of it. So last one that we're going to do before we start getting just some nice standard shortcuts for ourselves to use is I want us to consider the following. Let's do a function that's not awful. Let's say that f of x is equal to 3x squared. What I want us to do is find and graph f, cap f. Now, for these, we're going to get something that we've never had to deal with before, but we're going to see it happen right now. First step is if I want to find cap f, what's a question I'm asking myself? One more time. So you're right. Cool. I'm okay with that. Find the antiderivative. Let's see if we can all do that first. If we can't, I'll come back because that's not exactly what I was expecting, but that's what it is. I'm asking you to find and graph the antiderivative. Try to find the antiderivative for me real quick. Once you get it, if you can give me a thumbs up just to say, yep, I got it. Or if you say, oh, I don't really get it, and just give me a thumbs down if we're not quite sure, and we'll come check. What do you think it is? Love it. Almost. You're missing one thing. Love it. So walk me from here to here. What did you do? So I'm going to make a claim here. I think that you actually just took the derivative again. So instead, the question should be not what is a derivative of this, but what function has this as a derivative. So it's not this, because this derivative is 6. So you've gone the wrong way. You found me another derivative. Love it. Love it. Love it. Love it. I already loved it. Love it. Cool. So check it out. Right off the bat, if we're thinking about the antiderivative as a whole family of functions, let's do that. First and foremost, what is cap f? Now, I can't really draw infinity, not all infinitely many of these, but we can hopefully agree that there is a way to think about this. Do you guys know what the graph of x cubed looks like? Do you recall? So I know it does this. Anything else about it though? It kind of looks like tangent. It's just like straight up and down. So if we wanted to think about what's actually going on here, let's have it. Let's graph it. So quick and easy graph. Now we're actually just going to sketch it just so you know. So here we go. We have x and y, and we're just going to think about all these families. If we wanted to make a table, we could. I don't think we need it. Right off the bat, what's the easiest possible choice of C we could have? 0 would be ideal, right? So I know that there is one that runs through 0. And I'm going to switch colors here. But I know that, at least at just sketching it, this is what the graph of x cubed looks like. Roughly like that. And it doesn't curl back in on itself. It keeps pushing out. So about like this. That's one of the functions that works, right? This is x cubed plus 0. Give me another one that works. X cubed plus 1. And I'm actually going to cheat my way through this. We're going to say that that's the same. And check me out. We're getting crazy. Does this also work? Does this work? Oh, sorry. Gotta unclick it. Does this also work? All of those? And how many are there going to be realistically? Infinitely many. And we can sketch them all on here. They're going to show up. And we're not quite at the point where we're going to be able to like really make nice sense of these. And I can't undo that one, unfortunately. But there's infinitely many of these things going forever. Now, when we have infinitely many of them, we're going to see here, you guys have all looked at windy.com, right? Like when you're looking at the winds, we have like small little vectors that say this is the direction that stuff goes. If we said, for whatever reason, in some problem that we're trying to solve, that I know that the point 1 or when 0, 1 is on this graph, I now know that it has to be this out of infinitely many. If I said 0, 4 were on the graph, I now know it has to be this one out of all infinitely many of them. And if we have a little bit of the data, some of my initial conditions for like a real world situation, we can pick out of these infinitely many, which one will it be? And it allows us to it allows us to start solving problems using these graphs that maybe we can't actually solve algebraically, but we can actually solve them and make sense of them with this bigger idea behind. Now, that's where we're going. We're not going to be doing like Maxwell equations and things like that, which is its own standalone thing that you would cover if you're doing hardcore physics. But we get that underpinning, like the bottom part of it today is where this all starts. Okay, big ideas living here. Should we take a really quick break? Too bad, just kidding. All right, quick vocab. I haven't even looked at the word. I have no idea if I've seen it. I don't even know where my calendar is. So we'll see if that works out. Ooh, should we show, rather than doing the vocab, do you guys want to show Miss Sweet a quick round of bowling? Like the real bowling or math bowling? Oh, you're going to love this too. I also love real bowling. Okay, who feels confident in your ability to explain it? You think you got it? Really? Is it because you don't want to talk or you really don't think you can explain it? Okay. So I don't know why it'll. That's a good point. All right. So check it out. We have these nice antiderivatives. We are going to try to build up a rule, and quite a few rules realistically. We will work out like the bigger limit ideas here, but for the nice antiderivatives, nice quote unquote, I want to see if we can find them. So for this, if you're on the back side, I might encourage, like if you're on the bottom part of a page, we're about to make a list that has quite a few. If you have your textbook handy, and I just will show you real quick, I don't want you to actually open your textbook, but of all of our nice derivatives, there's roughly 25 of them. This is the list that we're going to be building, where we have the function and its antiderivative. I know you can't read it. It's because I don't want you to have to read it right now, because I want to be able to think about a few of them before we just look at the table. So if you have the book open, I'm totally cool with it, but try to answer these before you just look and copy out of the text. And let's see where we're at. So last example, and this is probably going to be the last one that we do today. We'll see. I want to see if we can find antiderivatives. And I'm going to start shortening. Anti-DDX, I think, is a reasonable way to write antiderivative and save ourselves like 9 letters. My first several years, we use the anarchy symbol for this instead, which is pretty metal or punk. I don't know. What I know is I want you to find cap F if I give you the following. F of X is K. This means or implies to us, and I'm going to use imply, that cap F must have been something. Who has a derivative that's K? K's derivative is 0. Whoever whispered K confidently, but I like it. A derivative that is just K. What if I said the derivative is 5? Can you tell me what function has a slope of 5? What is it, Rafa? 5x. If it's 6, then the derivative is the slope of 6, and it's 6x, right? What if it's K? Kx, but you've only given me one of infinitely many. Kx plus c, and look at that, we get it. Kx plus c. And we have it. I'm going to make that capital, and it's super counterintuitive for me to do that. But we have it. Okay. Well, nothing too crazy there. I'm going to give B and C and D up here, and I want to see, you guys will see a trend, but I want to generalize this together. We're going to build up. If f of x is k on the first one, then on the second one, f of x is kx. And on the third one, f of x is kx squared. And on the fourth one, and it's the last one that we'll do of this type, we're going to do kx cubed. I'm going to give you guys a few minutes. I want you talking with one another, see if we can't figure these out. And then just so you know, this is going to end with a generalized rule. So I won't do E, but it will take us into a shortcut that we will use. I'm going to give you guys a moment, play around with them. Now, the most common wrong answer, and I'm going to show you, there's a couple different ways to think about it. With the exception of one mistake that I think was identified and fixed, I'm going to switch this question just a little bit. It's the exact same question. This is linear, right? What type of function has a linear derivative? A quadratic. And just like a cubic function has a quadratic derivative, or a quartic has a cubic, it just goes one down, because the rule for the derivative is subtract 1 from the exponent, and it just goes 1 degree less. So the most common incorrect version here is f of x equals kx squared plus c. You're not alone, because I think that face made me think you got it wrong. You and like 90% of people, so that's okay. Like, don't stress about it. You are almost right. Remember, what's the relationship between little and cap f? How do I move from this, like this is the antiderivative this way, right? So what's this direction? The derivative. Let's check just to see if there's anything wrong. Let's differentiate kx squared. It's 2kx. But I don't want it to be 2kx, I want it to be kx. It's multiplying by 2, right? If only there were a way to undo a multiply by 2. Divide. I think that we can fix this if we just say this is over 2. Whose derivative is x squared? X cubed, right? But the same thing is going to happen here again. If we just say it's kx cubed plus c, that would give me 3kx squared. But I don't want it to be 3. I just want it to be k. So if it's multiplying by 3, if we do the derivative, how do I undo that? Divide by 3. Huh. What sort of function has a derivative that's cubic? The fourth? So kx to the fourth over what, do you think? 4 plus c. And we can check these. Now, there's some wonky stuff that could happen. Nobody's asking it here, and that's fine. You can't really tell if I divided everything by 2 or just this, right? If I had done the following, and we don't have to here, but I just want to start introducing this strange idea. I might have divided everything by 2. Like, I don't really know. Are you okay with that? What's a constant divided by a number? Is it still a constant? So even if I divide it by 2, could I still just call it C? Because a constant, if you add a constant to a constant, you just get another constant. Like all these things, you don't really change it. Maybe we'll have to use some subscripts. Let's get one more. And this last one, I'm going to call it not E, but instead we're going to call it generalize. And it's the last of this little piece. I want us to go one more. And this is going to be a big statement. If f of x, little f of x, is equal to x to some number a, then its antiderivative is, and I'm going to write it right here, and I want to see if we can't find a rule. We are just looking for the powers of pattern recognition, which is a pretty awesome thing for humans to be looking at. On A, there's no x here. Could I write an x to some power in here if I really wanted to? It could be x to the 0. So let's just look at just the powers first. X to the 0 goes to x to the 1, and then I didn't write it, but could I put over 1? Okay. X to the first goes to x to the squared over 2. X squared goes to x cubed over 3. What about x to the a? What's happening when I go from a function to its antiderivative with respect to the degree? So adding 1, subtracting 1, or nothing changes? It always adds 1. And then we divide by what? It's a plus 1. Now, plus c. And here's the really awesome part where we're going to see all of a sudden, they don't really feel the exact same. Like when we talk about it as an antiderivative, the connection between a derivative and its antiderivative is super duper clear. When we make the transition to this idea of integrals, that connection is not going to be quite as clear, but we're doing that right now. We're just making this connection exist. I'm going to do some scratch work off on the side real quick. Remind me of the derivative rule. For the derivative, and you don't have to write this down, I just want to think about this. What's the derivative of x to the n? So nx to the, so let's see, I'm just going to follow this out. If we're doing the steps, we really just multiply by n. That's first step, right? Mult by n. And then we have new power is n minus 1. Everybody agree with that? What if we wanted to undo this and work exactly backward? And instead of saying the new power is n and we subtract 1, what's the opposite of subtracting 1? Adding 1. And then what's the difference of dividing by n? Or sorry, gosh dang it. What's the opposite of multiplying by something? Dividing. We're just working backward through it. We have some small changes that exist, but this will always be true. Now, this is really and truly a theorem. This is our first shortcut for finding antiderivatives. Now, some properties of these guys, and we're going to look at a few of them today. Your homework is going to be very different than normal. Does everybody agree that this is the rule that's happening? Like we can see that pattern emerging in this process. Okay, so we get 2 theorems real quick, and then I will advise you, and I'll tell you what I want you to do for the homework, but I don't want to have to write it all, and I think that you'll appreciate that. But let's see. We get 2 theorems right now before we're going to separate from one another. Now, the theorems that we're looking at, there's 2 of them. These are really just the properties of antiderivatives. So some handy properties. Of antiderivatives. Cool, cool. Now, very, very first, and I'm going to try to make these a little bit shortened We can make them more rigorous if we need to, and we will eventually, but I just want to propose it without naming it. The first one is if I have some function, let's say that h of x is f of x plus g of x. And I'm going to make it plus or minus just so I can cover both ends of that spectrum. So we have some function that's just the sum or the difference of two, or it could be more functions, but we'll just say two for now. What do you think that if this exists and the antiderivatives also exist, and I'm just going to assume that's true, what do you think we'd say h of x is? Cap h, I suppose. Cap f, and I'm going to do some weird stuff here, and I want you guys to decide, like, wait to write all of this until you're done, and I'll even write the weird part here. Do you guys agree to be plus c right here? And if you didn't have it, I wouldn't necessarily like erase stuff yet. Plus, what's the antiderivative of g? Cap g plus what? Plus c. And then this is that same idea that we talked about a minute ago. And I'm going to make it plus or minus because, Rafa, you were correct. If I have this constant and this constant, is there a more concise way we could say this? You could say 2c, but is 2c still a constant? Could we just say c? A constant plus a constant is still a constant, which means we can simply say that, hey, it's exactly cap f plus cap or minus cap g. And then we'll just add a singular constant c on the end, because it doesn't really matter what they wind up as long as they're both just real numbers. All that this is telling me is that if I have the antiderivative of a sum is it's been a while since we had to do these. The antiderivative of a sum is the sum of the antiderivatives. It works just like limits with derivatives. Of course it does. It's the same thing. We're just going the opposite direction. Okay. It's also true of the difference, but I don't want to have to make that big wordy statement if you're cool with that. All right. Let's get one more. Cool. This one may be even a little bit easier. I'm going to do a different shade just so it stands out. Purple? Do those look different to you? Now they do. Kind of. Not so much to me. That's all right. Okay. Last one. Let's say that if, and this is going to be an if-then statement. Maybe. I lied. Let's say that g of x is equal to some constant k times f of x. Then, what do you think cap g is? Guts? Intuitions? K cap f plus c is a natural thought. I agree with you. Nice job, Fern. What is this really highlighting? This says that I can just take the sum or difference of the antiderivatives. That's nice and easy. This one is saying constant multiples essentially just do what? They stay, right? They just factor out to the front just like they did with regular derivative stuff. We'll just treat constant multiples as constant multiples. Okay, here's what I want you guys to do for your assignment tonight. And we're going to take a quick check on this tomorrow. I want you guys, either in the form of flashcards or in your notes, I want you to look over table 6 on page 364. And tomorrow in class, we'll look at just some of the weird ones. But what I want you to do, and I wouldn't necessarily suggest all of these in your notes, but you guys remember how we did that sweet derivative quiz and said know all your rules? Well, I bet we can make an equally sweet antiderivative quiz where I want you to know all of the rules. They're not different, just so you know. Whether it's flashcards, in your notes, something, I want you to go through here with the following exception, put asterisks next to our shine and cosh, because those are hyperbolics and we don't deal with them in here. But I want you guys to go through this list. Here's my challenge. Some of them you're going to be fine with. I'm confident of it. If you know your derivatives, the antiderivatives are going to be easy. Sines and cosines and tangents, they do some nice stuff. I want you to make flashcards or write down the ones in here that are weird for you. The ones that you think you will not remember off the top of your head are the ones I want you to write down in your notes this evening. Instead of an assignment, you guys are going to take this table and add whichever ones you're worried about forgetting into your notes. Cool, cool? All right, baller. You guys have a wonderful day.